Okay, so let's go through this homework. First, when we look at number 5, we see that we want to expand this log. So we know that division turns into subtraction because of our log properties. And then this multiplication turns into addition. But here we have to be careful. We're subtracting this big piece. So if we break it apart into 2 smaller pieces, then we must subtract both of those. So this negative distributes at both of these, really subtracting these 2 small pieces. So we get this minus this minus this. And then the last step when we expand is always to pull those constants out front. Here, let's see. Interestingly, here when we were expanding, I decided to pull that 1/4 up front first. You don't have to. Here I did it just to make things a little easier. So it's 1/4 times all of this stuff. So we're just going to have to be careful here, yes? So it's going to be 1/4 times all of this. Well, then it's 1/4 times all of this. The natural log of a fraction, that fraction is going to be subtraction. And then this is a product. The natural log of a product is going to become a sum. It's really minus all of this. So my negative hits this, and my negative hits this to give me this. But then the last thing we do is pull down these little exponents. I get this, and I can distribute through my 1/4. I get that. Okay, so that's 5 and 7. If you look at 11, now we're trying to condense. So the first thing we're going to do is pull in all these exponents like so. But then here, this addition, because of log properties, because a log is just an exponent, becomes multiplication. And then this subtraction becomes division. So log of something minus log of something else, we just divide. Okay. Notice how it's really clear to follow my reasoning. All my equals line up. It's easy to read. 23. So now we're trying to solve, and we remember that solving means I need a solution to the equation, a value that, when you plug it into the original, makes it a true statement. So up here, when I see this, I wish I had the natural log of A equals the natural log of B, because then I could say that A must have been equal to B because natural log of X is a 1-to-1 function. That's going to be the big key idea that we use here. So to get natural log of A is equal to natural log of B, we'll take these two and combine them. So addition becomes multiplication. And so now I have the natural log of something is equal to the natural log of something else. And the only way that that can happen is if the inputs were equal, and that's because natural log of X is 1-to-1. So then we distribute here and get this, and then we get all the X's on one side and divide. So we get X equal to -7. Look at 29, pretty similar. We just want to get all the logs on one side. So if we move this over here, the reason is now we have a sum of logs that I can write as the product for a single log. But now there's an understood base 10 here. So this and this are just the same thing, but now I recognize that this is in log form. So I'm going to put it in exponential form. So 10 to the first equals this. Have that right there. Then if I distribute this, expand this out, I get this. And now I have an equation that I need to solve. And we know that the key way to solve an equation by hand is to set equal to 0 and factor, because we're going to use that 0 factor property. So we get everything equal to 0 and I factor. Well, I can't really factor, so I end up using the quadratic formula. Okay. Then you get -1 minus a root over 2. That's going to be a negative number. And when you try and plug it in back over here, it's not going to work. So -1 plus that root over 2 is going to be the only actual answer. The negative solution is just what we call extraneous or extra. and not in the good way. So 33, if I'm trying to solve this big ugly equation, well, I just want to change the form. So quickly I see that 3 to the third is 27, so that can be replaced with 3. And then 5 raised to the log base 5 of 1. This log and 5 cancel out in a sense and give me 1. And then 3 minus 1 is 2. So I have this. Well, then it looks just like a problem we did a second ago. So if I get all the logs on one side, it looks like this. The log of a sum, the sum of logs becomes the log of a product. So now I recognize this as exponential form, and I can change it into, log form, and I can change it into exponential form. Right? And so then now I have an equation I need to solve, and we know that the main way to solve an equation by hand is to set equal to 0 and factor if you can at all. So set it equal to 0, try and factor, I can't. So again, I have to use my old buddy, the quadratic formula, because it's a quadratic. If it was a cubic, I couldn't do that. We get our answer, 3 plus the square root of 10, similar to last time, only the positive answer makes sense. 56, they say that this is our equation for an initial amount of pollution. You give me a time and I'll tell you how much pollution is left. So they want to know, when will we be down to 1/2 of the original amount, or 50%. So that means I can replace the output with 1/2 of y naught. So now here's an equation we need to solve. The way that you solve that sucker is to divide by y naught. Cancels out. And then from here to here, I take ln of both sides. So in other words, you plug them both into the natural log function. Get this. Natural log of e to the stuff. Natural log of e to the x is just x. As a property of natural log. Then you get t is approximately equal to 1.814 years is when you're going to clear out 50% of that pollution. 57, Rx is our response, where x is our stimulus. If we have, remember, x naught is that threshold value. So if you put in a stimulus of x naught, then x dot divided by x naught, all that just becomes 1. But log base 10 of 1 is just 0, so you get 0. What does that mean? That means your response, if you're at the threshold level, is nothing, because I haven't felt it yet. It hasn't gone over the threshold. Then it wants to know what happens if you give me 2x, what happens? Well, if I put in 2x here, I now have this value, and notice what I can do. I want to get this in terms of my original. My original is a log of x over x naught. So if I factor out this 2, I can think of this as 2 times x over x naught. I have log of 2 plus log of x over x naught. Right? I'm going to think of it as this times this. That's why it becomes plus. But then I can distribute this a, and notice what I have really quick. It turns out that this is just simply r of x. So now we can think of r of 2x in terms of r of x. So when you double the stimulus strength, the reaction goes up by a log of 2. Isn't that interesting? And that's it. Have a good one.